So this is, I hope, reasonably short. And so now people are, most of them I think are logged in now, and the other ones will get. So this is the last lecture for me now, just to wrap everything up. Of course, there will be one more by Dr. Noemi Friedman on how to do Bayesian updating and things like that numerically with the SGLib. But now a little bit of sort of philosophical things on why we do all of these things. Okay. Good. So a little motivation of what we're going to talk about, and then the topics will be, I want to talk about the connection between risk and uncertainty, and why do we deal with uncertainty. It has to do something with risk and decisions under uncertainty, which are risky, okay? And why we want to update our knowledge and how to determine risk and what is risk and so on, okay? Good. So it's not going to be very technical, and so there's not going to be much mathematics in this one here, okay? Good. Let's start with the motivation. So what we're worried is about here that we have mathematical models, and these mathematical models, we hope that they are model aspects of reality of the real world, okay? Be they a model, an engineering model of something, a machinery or a building or a dam or whatever, or a model of part of the environment like the aquifer I'm using the whole time as an example, or for instance, the climate system of the whole planet, you know, in a climate simulation or whatever. So the mathematical models, which model aspects of reality, okay? And then on the other hand, we have data, observations, and measurements and all this, okay? And what we really want is a future. We know that mathematical models is another way of expressing knowledge, okay, about certain things. A very concentrated and distilled way of representing knowledge. And the data, of course, are also knowledge. We know something is a certain, for instance, with weather prediction, we know the temperature today is, I don't know, 18 degrees or something like that. It's probably colder here right now, so only 15 or something like that. This is also knowledge, okay? And we want to put these two things together, okay? We have to see, first of all, that models are not perfect. They contain aleatoric randomness, and they contain uncertain quantities. And also what they contain is a model error. They're typically not perfect, okay? And models are used to explain or understand or predict or determine effect, okay? For instance, you want to predict what the weather is tomorrow. So that's one way of using the weather simulation, or you want to predict what is the climate in 100 years and use a climate model for that. Or you want to predict how does this bridge behave when a heavy train goes over it. Yeah. So this is the prediction. Or you want to understand why something is happening, okay? Or you want to explain why something happened, okay? For instance, you want to something, let's say something has broken, a bridge has cracks or something like that. So you want to explain and understand why this happened, okay? So you want to use the model for that. But in the end, there's often a kind of decision to be made. Typically with predictions, you make predictions to make decisions. You typically don't do them just for fun. So I want, for instance, the weather prediction for today. So I know whether I have to take an umbrella or not when I go out. So that's why that's a decision which I'm going to take. And it's a decision under uncertainty because I'm not certain. And the weather prediction has different degrees of certainty about is it going to rain in the next couple of hours or not, okay? But this is what I want to use the model for, okay? And so that typically gives you more than just the data. Right? You can see this with weather predictions. So the data, they have the data, okay, other than satellite data, they had the data already 100 years ago, the data from meteorological stations or whatever. But just with the data doing the weather prediction and now doing with mathematical models, you see a big difference. The weather prediction has become much, much more accurate in the last 20, 30 years than it was then, okay? Good. So then they could just say, tomorrow maybe it's going to rain or something with a certain probability. Now they can tell you where it's going to rain and how much and all these things, okay? So this is the value of mathematical models using the same data. Good. But each decision, now coming back to the decision making, to determine effect is also a decision to say this is because of this or something like that. That's another kind of decision. Each decision carries a risk, okay? For instance, that you think that it's a wrong cause that caused something, or you make a wrong prediction. So, yeah, I don't take an umbrella, but it's going to rain, for instance. So that's a certain risk which comes with the decision, okay? And the models are used to gauge the different outcomes, okay? Good. So now we're going to talk about risk. What does it mean, okay? Always, it's a good idea always to look at the history of these things, okay? So let's look at the origin of the word risk. It turns out that the origin is uncertain. What does risk come from, okay? Where it first appears, what we can see today in written record, so we don't know whether it's used spoken, as risico in Italian. And this was used in trade and economics, okay? So this some risico appeared there. So there's versions which connected with the Arabic word risk, or risk, which means livelihood given by God's mercy. So again, something which is not under your influence, but under God's influence. Okay. Other versions connected with the ancient Greek risikon, and this means cliff. Okay. And in Vulgar Latin, resecum means a rocky cliff. Of course, these things are risks in today's meaning for shipping. Okay. So, and of course, for cargo ships, then this is, you can see the risiko can come from that. So it can come from any of the three. It's not quite clear. Okay. It was mentioned already by Christian Huygens. Huygens also was one of the early scientists who did something in probability theory. I didn't mention him. He was before Jacob Bernoulli. Jacob Bernoulli, if you remember, was the uncle of Daniel Bernoulli. Daniel Bernoulli is his nephew. Okay. And Daniel Bernoulli treats something which is called the St. Petersburg paradox. I'll come back to that. He lived in St. Petersburg. That's why he called it it's called the St. Petersburg paradox. So we'll come to this later, okay? So today, the Oxford Dictionary, if you look in the dictionary, the Oxford Dictionary tells you risk is the exposure or the chance involving the possibility of loss, injury, or other adverse unwelcome circumstances, okay? And of course, if we want to deal mathematically with it, that this is not really helpful, or a little bit helpful, but we have to find a mathematical formula. But it's not unique, so it's uncertain what to consider as risk. Okay, so what is the modern usage? There's actually a norm, an ISO norm for it, ISO 31000, and a guide. And today it says risk is the effect of uncertainty on objectives. So you see how it's connected with uncertainty. It's not really mathematical, but it's the effect of uncertainties on whatever your objectives are, okay? Previously, in 2002, so this is from 2009, in 2002, it meant the combination of an event with its consequences, okay? An even older one, which is still used today, often in engineering, is the probability of an event times the loss, okay? So you could say, if you sum this up over all probabilities of events, that's the expected loss. That turns out to be, and it's very known for a long time, that this is not really a good measure. First of all, because the loss, in this way we model it, the loss is going to be a random variable. And just judging a random variable by its expected value only is not a really good idea. But unfortunately, in engineering, this is often taken as risk. That's okay if the variation, if this random variable, the variance of this random variable is small, then it's okay, but otherwise it's not. Okay, and it can be completely misleading. It was already shown by Daniel Bernoulli, who I mentioned just before, in the St. Petersburg paradox. That this is what this paradox is: that the expected loss, in this case it's a win, is infinite, and still you wouldn't do whatever you're required to get this win. Okay. It cannot be, so this is an extreme example, that's why it's called a paradox. So the expected win is infinite of playing a game, and you still wouldn't do it. Okay, I will come to that back later, how this happens. And this is by not looking at the variance of this random variable, but only at the expected value. Okay. And you can just say actually expected value is infinite, so it actually doesn't have an expected value. So it's a wild random variable in this way, and then you can't judge it by this way, okay? So uncertainties include events which may or may not happen, uncertainties caused by ambiguity of lack of information, and that's the one we dealt with, okay? So this is aleatoric uncertainty, event which may rain tomorrow or it may not rain or something like that, or something caused by lack of information, okay, lack of knowledge. And of course, it can have negative and positive impacts on objectives. You may win in lotto tomorrow, so that's certainly not a negative one, okay? And it's used in many different areas, not just in engineering, economy, health, information technology, insurance, business, psychology, and so on, okay? Good. So the beginnings of probability, there's a picture of Christian Huygens. The beginnings of probability actually were, again, I say they're connected to games of chance. And by the way, it's quite interesting. So this is typically what's considered aleatoric uncertainty, which happens there. If I throw a die, will it show a 1 or a 2 or 3 or a 6 or whatever? Okay, or if I draw a card, what kind of card is it? This is considered aleatoric uncertainty. Although there's people who know how to trick this a little bit, but it's typically considered as aleatoric uncertainty. And this probability was called chance in that time, okay? This was called chance. And what we today call epistemic uncertainty, probability, that's what's called probability by these guys, okay? So this is the change, the language has changed in the meantime, okay? So, and what is uncertainty? And there's very different attitudes of what uncertainty is. We looked at uncertainty, it's something which you can model with random variables, with probability or whatever. But this guy here, it's the economist in the US, in Chicago, Frank Knight. What he says, I read it now, uncertainty must be taken in a sense of radically distinct from the familiar notion of risk, okay? From which it has never been properly separated. It will be that a measurable uncertainty, or a risk proper, as we shall use the term, is so far from different from an unmeasurable one that it is not in effect an uncertainty at all. So what he's saying is, if you have an uncertainty which can be somehow described with terms of probability, then it's not really a risk because you can factor this in. Yeah? For instance, for safety, I may take an umbrella with me, although I don't need it in case it rains tomorrow. So it's something I can hedge against, okay? But there may be also a tornado tomorrow, which I don't know, and my umbrella may be blown away, I may be blown away, okay? So this is this risk which I don't know. This is this uncertainty which he considered. So you cannot say you cannot be certain in any way about uncertainty. He has a very, very extreme view of uncertainty, okay? And so there's different names to this, the uncertainty, intangibles, imponderables. So this is the hardest to define. This is the uncertainty which we don't know, okay, which he means. This is the impossibility to accurately describe present, past state or future outcome or whatever, okay? And this has been shortened famously by Donald Rumsfeld as when he was Secretary of Defense in the US, and he was asked about something about the Iraq War, okay, and he talked about known knowns. So these are things you know for certain. Actually, in a strict sense, these are facts, so to speak, what we call facts, okay? In a strict sense, of course, these are only mathematical truths. Only those you know for certain. Everything else, your eyes may be deceiving you or whatever. So, but it's typically to mean facts, things we know for sure that they happened or whatever. It was like that or something like that. Okay. Then these are the known unknowns. That is what Knight called risk. This is the uncertainty we dealt with. So we know it's uncertain, but we know how to deal with it. Okay. So we know how to describe it in terms of probability or whatever. And for him, he's an economist, he says you can hedge against this. That's not a risk at all. Okay. So that's what's called risk. But the uncertainty, he calls something different from risk. Okay. And these are the unknown unknowns. This is what Knight calls uncertainty. This is what's just on the previous slide. So this he calls risk, and this he calls uncertainty. This is something you can describe with probability, and this you cannot. So this is things which we have not modeled. And if we're talking about mathematical models and modeling things, uncertainty with random variables, these are things which we have not modeled, okay? And as I say, like with whenever something happens which you didn't expect, you didn't know this could happen. Okay, these are sometimes very rare events. Okay, sometimes you probably have heard of black swans. They sometimes subsumed under this. Okay, that's a big problem on how to deal with this. Now you see that these are combinations of known and unknown. So typically people speak only of these three, but there is another one, unknown knowns. This often happens when people discourse about something. This is certain preconceptions which people don't discuss because they all have them, but they're preconceptions. They may not be true, okay? Or they don't want to discuss them because they just want to impose them on you. That you accept something as fact which is not necessarily a fact, okay? And something which is not being discussed. Okay, so this is something you have to watch out. So this can happen too. Okay. Good. So if we look at uncertainty, what people have classified uncertainty, okay, then we've actually talked about here, about this, about objective uncertainty. And you see there's epistemological, epistemic uncertainty and ontological uncertainty. This you can call the aleatoric uncertainty. And in subject uncertainty, like how should you decide? There's moral uncertainty, maybe. Is it morally right, your decision or not, or whatever? And does it violate any rules and things like that? Okay, so we are only dealing here with this kind of uncertainty right now. But I just want to point out there's other ones. If you have to make a decision, there may be this one here. Is it morally acceptable, your decision, and so on. So this enters in this too. Yeah, okay. By the way, of course, you can say, well, the course of the universe is, I believe the course of the universe is determined, and everything what happens has been determined already. So it is just like a movie what we're living in here. Okay. And of course, we cannot decide this question. Okay. But this accounting for uncertainty doesn't mean deciding this question here. It deals with the fact that we cannot predict the future. Okay, so we at present time, we don't know exactly what's going to happen. We don't know exactly what happened in the past if we haven't been there or something like that. And this is the uncertainty we're dealing with. Okay. Good. So other connected things which maybe is damage and hazard. Okay. So what is damage? And so with damage, this has to factor somehow into risk. You lose something. Okay. So it's a loss of life or impaired health or financial loss, property damage in monetary terms. Okay. Or a lost opportunity. Yeah. So you call this opportunity cost. Because you did this and this, you couldn't do this and this. Because you bought a piece of bread, you couldn't play lotto and win in lotto. Okay. But it could be cultural damage, damage to historical monuments or whatever. It's very hard to measure them in money, for instance. Okay. And so this all depends on the social valuation of these things. Okay. So this is all what you call damage. There may be very different kinds of damage. Often it's only looked at damage measured in monetary terms, but many things you cannot measure in terms. It's damage to threats, to health and life and so on. It's very hard to measure this in money. Okay. Good. And hazard, it's the potential to cause harm. Okay. So this apparently comes from the Arabic word azar, which means dice or die. Okay. I don't know whether it's singular, plural in Arabic. I'm not that good in Arabic to know that. Okay. So, and then measuring damage is an economic or sociological task. You can see all these damages, they're in different terms. And if you read about it, so if someone does it in economics, it's typically done in monetary terms. That's what you most often see, but it's very difficult to measure all these things in monetary terms. Good. And connected things are vulnerability and fragility and robustness. Okay, so what is vulnerability? This is the susceptibility to damage, or the possibility for a hazard to cause damage that you call vulnerability. Okay. And fragility is sensitivity. So fragility is something a situation which works well if it's exactly like that, but you change it a little bit, then you have a large damage or a huge change or whatever. This you call it fragile. So fragility, you would typically, if you build something, you want low fragility, okay? And then, of course, you want to have situations where there's low vulnerability, of course. So you don't want to put something where it's highly possible that it gets damaged, okay? And robustness is the ability to cope with variability, okay? Good. So now if we model a system, we model it in mathematical language. Okay? We're talking about mathematical models, and the models is about different aspects. And there could be a hierarchy of models because there's different modeling errors. A simple model has a bigger modeling error than a more involved model, and so on. You all know this from already from your experience. You model something very easily and not so with more. We're talking about finite element models. It's typically for instance, if you use more elements, then it's a finer model, okay? And it's typically better, the response. And we hope, otherwise the finite element model isn't good. If you increase the number of elements and the response doesn't get better, then there's something completely wrong with your model, okay? And we want to transfer these models typically to a computer. Now, this is logic in silicium and software, okay? And to run it there, so because we can't do the computations by hand. It means the models have to be approximated numerically, okay? And then there's an approximation error. And the hierarchy of models, they may be for different scales. I've already showed some models for multi-scale things of materials, okay? Or maybe at different aspects, and they have to combine them, lead to multi-physics models and things like that, okay? So this is all the things which appear in modeling systems, and there's everywhere there is potential for uncertainties, okay? Okay, so and then what we want to do, and this is what we want to talk mostly about the TOSP, we want to be updating the uncertainty. We hope that if we learn new facts or measure new things, get new data, obtain new observations, or whatever, that this is additional information, and that the representation of uncertainty, so we're only talking now about this uncertainty which can be represented. We cannot talk here now about the uncertainty which we haven't thought of and which we haven't modeled. That's typically not in the model, okay? But of course, in real life, those things can happen too, okay? But this is not in our mathematical model. And the probabilistic description allows such updating, okay? Many other models, we talked about how to model uncertainty, and there's models of uncertainty where, for instance, this interval description of uncertainty, that's an extreme case of a probabilistic description, but it's so simple that the updating doesn't do anything, okay? If you try to update that description, it just stays the same. You do it via Laplace and Laplace. So you have to either find other ways, and then it's the question, are they coherent and consistent? Okay, or it doesn't work. For instance, for fuzzy descriptions of uncertainty, it's very hard to see on how you can do things like that. Okay. And there's other things which you want, of course, with a description of uncertainty, and you want to be able to tell what to expect. Okay? And you need something like an expectation operator. A probabilistic description has both of this. Okay, and the way to do it via Bayesian Laplace, we've looked at this now and extensively in the course, is to change your description as little as possible. That's why we used for conditional expectation this least squares ideas and things like that. This is to have as little change as possible to be consistent with the new observations and new data. And if you look at the Bayesian theories were invented more than 250 years ago at incredible ups and downs, okay? And there's actually a little book about this, if you're interested to read it. It's called The Theory That Would Not Die. I think that's what it's called. The Theory That Would Not Die. Because there was a time in probability and stochastics and statistics really where people tried to kill Bayesian thinking, to rule it out, so no one should do it. It was verboten in German, which means forbidden. Good, but luckily it survived because it's quite useful. Good, so just now it's a little bit of mathematics. Remember our little example of our aquifer, we formulate it like this, and in a abstract sense we formulate it, we have an extended state, which is the state U, plus the parameters which we don't know, which I describe as Q, I call this Xi. And then we have something, we advance from one observation to the next one. We have a way of telling how this will advance, okay? So this is what our mathematical model does for us. It tells us either how to do the updating or how to change the state or whatever, okay? Or both, yeah? And this is our mathematical model for the system observed at times Tn, okay? And then there's quantities of interest. These are functions of this extended state. We've seen this to here, just to remind you. So this is a function of the extended state, okay? And typically it's noisy what is being observed. So it's the function little h of the extended state and some noise variable, okay? And what we want an inversion of this function, and it's not invertible, and this leads us to the whole thing, to model the state as a uncertain quantity, as a random variable, okay? And then everything else becomes random variables here. And now it's an updating of this probabilistic information, okay? And the whole problem now luckily becomes well posed, which was well posed. So this is the main thing what we're doing. So we talked about the whole time and how to make these models. And all I talked about last lecture and yesterday is how to make these models nice. So the updating works and the approximations which we do work, okay? And to become a well-posed problem, so we can do this here on the computer. Only well-posed problem should be run on the computer. Anything else produces only lotto numbers. Okay, so what are the steps? So this is the wrap-up really of what we want to do. So we want to track this extended state, okay, and we track it by a random variable, okay. Part of it may be a random variable, but it's an aleatoric random variable. The one I'm talking now, the difference between here and here, is this epistemic uncertainty, okay? The state itself may be a random variable, but it's an aleatoric random variable, so I don't consider that part here, okay? Now, additional randomness or probability enters, and this is due to epistemic uncertainty. And we use observations to track this, okay, to get close to the real state with this probability distribution. So we have to prepare the prior. So with the whole thing which I talked about, how to do the Kahun-Lewis expansion or whatever, and things like this, how to model positive random variables. This was preparing the input. Okay, this is to bring our knowledge into a proper form for approximation and update. So it was best if they live in linear spaces and there's no constraints. And this is all about how to get rid of constraints and how to put things about in linear spaces. So once we have that, then we can use this here in the model, and then we can do the prediction or the forecast, like predicting tomorrow's weather. Okay, and I predict what the observation. So I predict what the weather will be at all the meteorological stations, what the wind speed, temperature, humidity, and whatever pressure will be there. Okay. Then, when tomorrow's weather arrives, they measure all this, okay? The meteorologists measure all this, okay? And then you would compare this here with this here. This is a random variable, and this is data, okay? So there's nothing random here. This is what the instrument showed, what you read from the instrument. And you want to use all that to update the state. And the filtering idea is to take the prior state, the forecast, and change it by something. And this is So this was called UQ, the uncertainty quantification. This we often call BU for Bayesian updating. And this guy here is called the innovation. So the innovation changes the prior to the posterior with what's called the assimilated state, okay? What we used here as loss function was the difference squared of certain things. It's where we computed expected conditional expectation. Okay, but you can use other loss functions here in the Bayesian updating. So if you compute this mapping here, if you construct this mapping, you may actually use other loss function. One example which I often take to show this. So I come here from northern Germany. I actually come from Hamburg, so that's close to the North Sea. And the North Sea is known for very violent floods which can happen there. Okay. So land is protected from these floods by dikes, okay? And these dikes have a certain height, so they've been raising these dikes in the last 20, 30 years by, I think, about 0.5 meter or something like that. And why have they been doing this? They've been raising the dikes because they expect that the sea level will rise, okay, due to climate change and whatever things, okay? And that maybe storms are going to get more violent and so on. So anyway, that's an expected value which they have, this 50 centimeters, what they need to, but you can see that the risk now, if you err on the wrong side here, for instance, and you build the dike higher than you should have, okay, then you spend more money than you should have, because raising it by 60 centimeters will cost more than raising it by 50 centimeters, okay. But if you don't raise it enough, you risk human lives and you risk property or whatever. So you can see that the deviations from the correct, so let's say the expected value to one side or the other side, don't incur the same loss. The losses are different. Okay, and then you might want to use a different loss function to compute what to expect. Okay, but for conditional expectation, we use the least squares loss function. Okay, and the others are possible if you want to put this decision making into the Bayesian updating. Okay, that's possible to do. Typically, people do that, by the way, they don't want to take only this decision because you have to take care of also of these unknowns, which are not in this model, okay? And that's why typically you want a human to take the final decision. Okay, so what is the uncertainty? Uncertainty is described by all possible outcomes of all the states of the world. These are all omega in this capital omega, okay? And then to formalize this decision-making a little, decisions under uncertainty, that's what we want to do is the possible choices, so our decisions, so this is something from some set of possible decisions, okay, which you can take. Different actions you should do or whatever. So they all come from a decision. You decide to do this and this. I decide to take an umbrella with me tomorrow, or I decide not to take an umbrella with me. I decide to dress warmly. I decide to wear just a short sleeve shirt or whatever because it's going to be hot or whatever. Okay, so these are decisions. But decisions under uncertainty involve costs when something really happens. So the outcome, what's going to happen, and the decision, though, together, they produce a certain cost. Well, the cost could be positive, that it's really a loss, or it could be negative, then it's really a gain. Okay. So, for instance, I play lotto. Okay, that's a decision I do. And one possible outcome is I win the main prize in lotto. Okay, so then the cost is negative. I've gained something. Okay, good. So these decisions, they generate benefits and they generate costs. Okay, and so I'm taking this. So costs are really something where you lose something, and benefits where you gain something. Okay, so this is making this difference. So my lotto win would be this. And if I don't win in lotto, I have a cost because I bought a ticket and it cost me something. Good. So now the cost and benefits, of course, if you want to make a decision, and the costs and benefits, they depend on the decision and on the outcome of the world. Okay, what state is going to be the world tomorrow? Okay. We have an unknown or random state of the world. Okay, so to each design and realization, there's an attached cost and attached benefit. Okay. And if we view this as random variables, the omegas, okay, then these guys are also random variables. For each decision, this is a random variable, okay? Typically, they have several components, okay? Monetary cost, lost human lives, destroyed environment, I don't know, whatever, cultural heritage destroyed and things like this, okay? So I just want to say not everything can be just one variable. So people, if they take one variable, they take this typically to mean money, okay? Then you can look at the effective costs, which are the difference. Money, of course, you can subtract from each other amounts of money. With lives lost, you can do this too, but with cultural heritage or whatever, pollution, it's difficult to distract something, okay? So, but this effective cost you can also call loss. Some people call that loss. So that's a possibility for a loss function, okay? But again, as I said, both cost and benefits have typically several components, okay? Either of different kind, okay, as I said here, or that, let's say, the monetary component is the costs to different groups in society. So this could be this cost to social group J, and this is the benefit to social group K, okay? Let's say someone decides to build a chemical factory right next to my house, okay? Well, that's a benefit to the owner of that factory. So he has the benefit. But I have the risk of living next to a chemical factory which may release a dangerous chemical. So I have the cost, a risk of something bad happening to me. And often you have it, and you see this in society with decisions have to be taken, that for someone, the benefit is good and much larger than all the other ones. But for many of the others, the costs are higher than for this one here, okay? So the group K has the benefits and the group J has the costs. And that's where many conflicts in society come from this thing here, okay? it's not easy to say what is of benefit to society or not. It's typically of benefit to one group, but not to another group and things like that, or to one individual, a group of individuals and so on, okay? For instance, you change the tax code, that's a decision to make, and you don't know what's going to be in the future, what the economy is going to be, but it will benefit certain people and it will disadvantage other people, okay? Good. So the risk is connected to the loss. So if we look at the loss as a random variable, then you see if we want to connect risk now to take just the expected value of a random variable, this is not really a good idea, okay? So we want a measure of risk. So it's typically a functional of this here, not just this here, but a functional of this. For instance, how much does it vary? Can it ruin myself? Okay, if I do an investment, okay, where it make a financial obligation, can it ruin? Can it bring me to ruin? Okay. So this, just taking the expected value, is typically not a good idea. So for each area of where you're going to use this, you have to think of what this is. What this functional is what you want. What is your quantity of interest where you want to take the expected value of? Okay. So as engineering, let's talk about engineering. As I said, the common thing was to take the expected value. And I already said that this is not a good idea. So many people still do this, but again, this is not a good idea because it's a random variable, and just judging a random variable by its expected value is not a good idea. Okay, just like an example, let's say we have costs, we have 3 different decisions which we can take, okay? And it's a random variable with equal outcomes. So as outcome 1, 2, and 3, okay? For this cost here, the cost for group A, okay? The costs are, when the outcome is -1, it's -1, the cost is 0, and here it's 1. Okay, if they have equal probability, I compute the average of these here. I get the expected value of the cost is 0. Okay, so I should be indifferent to this here. Doesn't matter what happens. Okay. Now consider situation B where this is not 1 but 10 to the 6. Okay, let's say this is dollars. Okay, so this is, you win $1 or you lose $1. The expected value is 0. You might say, it doesn't matter what I do, I'm just losing $1. The expected value is 0, so it doesn't really matter whether I play this game or not. Here, it's also the expected value is 0, but if you win, you're a millionaire. If you lose $1 million. Okay, so this can ruin you. Okay, although the expected value is the same. Everyone would say the risk is much higher here than it is here. So you can see that this cannot be the right way of doing it. Okay. So you need additional quantities or whatever, something to define risk. Just the expected value of the cost is not a good idea. You have to take this variation into account, okay? Good, so now let's discuss this for a second, expected loss and gain, okay, because it's still used to, so humans, and the other thing is humans are typically risk averse. If you look at how people take decisions, okay, they don't worry if it's a sort of uncertain situation where they can win a lot. Okay, so if the situation is I can win with this decision, I can win $1, and with a decision I can win $10, and with third decision I can win $1 million or whatever, then I can be very sort of, but this with $1 million has a low probability, I can still try to do this decision, okay, because I want to win. This is playing lotto, by the way, okay, so I can risk, the gain is big, but the loss is small, okay. If it's the other way around, people don't want to do it. So this is what you call risk-averse decision-making. Right? So it's a disproportionate avoidance of high loss. Because, of course, this can kill you. On the other side, it will not kill you. Okay, and it's similar with gain. So this is the St. Peter's paradox. So this is what Bernoulli wrote down. It was invented by his brother Nicolaus II. So there's some of them. They're all mathematicians. So there's a whole family of mathematicians. Quite a few of them were called Nicolaus after another uncle. Okay, so his older brother mentioned already. He wrote it down, so it's typically attributed to him, but apparently it comes from his cousins or brothers. Okay, so imagine an imaginary casino. He took it in St. Petersburg. That's why it's called the St. Petersburg currency. And the game is so that there's an infinite expected gain, which you can do, for instance, like when you're playing roulette. If there was no zero in roulette, okay, you just bet on red or black, okay? And every time you lose, you double your what you put on red or black. So you just bet on red. If you lose, you double the bet, okay? So at some point, you're going to win, and if you can compute what is the expected gain, it's infinite, the expected gain. But how much would you pay to take part in the game? So you pay a lot of money because you can win infinite amounts of money, okay? But it turns out that people are not willing to do that. Why is that? Because the expected infinite gain is not what you can use to decide this thing, whatever. Because, first of all, it can ruin it in between, because you have to double your bet every time at some point, and maybe more than you have, and then you're ruined, okay? And the other thing, because if you have billions already, winning another million is not very useful for you. The utility is low, okay? So he said the decision making is what Daniele Bernoulli drew out of it. He said you should consider utility in decision making, okay? Of course, there are other definitions of risk. In finance, they use something called value at risk. It's a certain quantile of the loss, okay? You're taking the loss as a random variable, you're looking at a quantile, we know what that are, okay? And they all hinge on this probabilistic description of way. So we can have a Bayesian way of decision making. I pointed this out already by taking other loss functions, okay? And in this way, decision influences the estimation of the probabilities, okay? But all these estimates are uncertain. And this is especially true what these things which are called rare events or black swans. These are often things which have not been in the description, okay? So all of these have been criticized. So you see there is not an easy way of deciding what is risk, okay? For instance, an airbag which works all the time except when you have a car accident. So that's not very useful, that airbag, yeah? Okay? But the value of risk would be small there, okay? Good. So let's talk about risk assessment and management, okay? So you have to manage risk all the time in your daily life. And you do this by living, okay? All the time you take decisions under certainty, okay? What we try to do here is to quantify this somehow, okay? But you see that the decision making is still difficult by saying what is risk and what is it we try to avoid, okay? So if you have faulty assumptions, this can lead to overconfidence. If you miss something, this is a black swan, something you didn't think of, okay? And this can often depend on the heavy tail of the distribution, okay? So a distribution where rare events can happen they have a big consequence. This is called the heavy tail of a distribution, okay? So losses can be huge, for instance. For instance, it's known that floods on the River Nile, they've been recorded through for the last 4,000 years, I think, before they built the Aswan Dam. And that's a heavy tail distribution, okay? So the flood can be very, very high, but with low probability, okay? So normally there's normative requirements. This is this moral thing which enters into decision making. So I will not go into that. Okay, but then we have the situation that risk cannot be quantified, but these are the unknown unknowns. So when we talk about decision making, we have to think of this too. Okay, this is what Frank Knight termed uncertainty. And there's the non-probabilistic methods, they don't produce a risk measure. Okay, so we have to fall back to hedge against this here. We have to fall back into simpler risk avoidance. Okay, so we have to accept that this is unknown risk. This is the unknown residual risk. But one example of to avoid this is redundancy. So maybe you know the saying, don't put all your eggs in one basket. Okay, because if you drop the basket, and if you all have the eggs in there, they're all broken. If you have them in several baskets, one basket breaks, you still have the other eggs. Okay. Good. So this is my last slide, and I'm finished with this. Are there any questions to this?
Well, I have a rather general question.
Yes, go ahead.
So you have shown a broad range of tools for dealing with uncertainties of the models.
Yes.
But what would be the first method to use for an engineer, the most robust? Where would you start?
Well, I think what you would use as engineers, you typically use mathematical models you predict, but you still have to think of the other things. Okay, so you want to build things so that they're not fragile, for instance. Yeah, so that they're robust. That's one thing, for instance, and this is known for any experienced engineer knows this is what you do it. You don't build something, and if the situation changes a little bit, it fails completely. That's what you don't want. You want, okay. And then if it fails, you want it to fail gracefully somehow, maybe. Okay, so it doesn't cause other huge damage when it fails. So you have to accept that everything's going to fail, but when it fails, you don't want it to have huge consequences because this thing failed. So this may be a way on how engineering design is done. And actually, experienced engineers, they design things in such a way. Okay. So that's one thing. But these are general rules how you go through life. Okay. And the people who don't, well, they fail at some point. Okay. Yeah. So it's very difficult to deal with these. About the known unknowns, this is what we told you on how to deal. And you have mathematical models. You can model this by probability, and this is what we told you about this whole course. Okay. But dealing with these unknown unknowns, making designs of engineering structures, let's say, from these unknown unknowns, well, you have to accept that they're going to get damaged or they fail or whatever. But you don't want them to build so that if they get damaged or whatever fail, they fail catastrophically, for instance. Yeah. Just as an example of this, yeah, talking of civil engineering structures, in the past, many structures were built as a statically determined system. Okay. Why was that? Because it was simpler to compute them, okay, typically. But this is not good. If you have a statically determined system, you know, if one member fails, the whole thing collapses. And this is typically not what you want. You want to make it statically indeterminate, then it has redundancies, okay? So even if you get a damage or something fails or whatever, it's not the whole system which fails. So one is redundant, and this is the other thing. If something gets damaged, the damage stays localized. It doesn't spread to everything else, okay? There have been tremendous, for instance, with this statically determined, there's been tremendous accidents which happened just because of that, okay? So that would be my, what literature should I recommend for further reading? I can look up some literature which I recommend. So do you mean literature on Bayesian updating, or do you mean literature on this risk and unknowns business and things like that? About uncertainty, about the uncertainty in terms of Frank Knight. Yes, I can give you a bit of literature on that, okay? But as again, so this is typically something which you already, if you grew to be 25 or whatever age you are now, this is something you probably learned in life on how to do this, okay? And people who don't learn it, they don't live very long, okay? So this is the Darwinian principle, so to speak, okay? So typically you're born with maybe or learn very early on how to deal with unknown unknowns, okay? But if you think of consciously about it, I think this is this here. So I'll try and give you some literature on this here. Okay, is there any other question which I can answer now? Adnan is typing. You can also switch on your microphones. Oh, when I will write my book, okay. Yeah, hopefully soon. But it will only be about the known unknowns. I don't think I will write about the unknown unknowns. Okay, so there's other people who think it's typically economists have thought about a lot about it this year too. Okay. Any other question?